Good morning to all of you. I would like to thank the Academy for giving this opportunity to speak here. The title of my talk is Phase Diagram of Strong Interactions. Strong interactions are one of the four fundamental interactions that occur in the universe. The other three being electromagnetic, weak interaction, and gravitational interactions. So I'll start with the phase diagram of water. This is plotted here, pressure as a function of temperature. This is one of the most widely studied phase diagrams in science, one of the most precisely known phase diagrams in science, and it is part of textbook. The constituents, the underlying interaction is electromagnetic. What we are trying to do in our field is try to lay down the phase diagram of strong interaction, the other basic interaction in the universe. It's often called as QCD phase diagram. QCD stands for quantum chromodynamics, which is the theory of strong interaction. The conjectured and experimentally realizable form of this phase diagram is temperature versus baryonic chemical potential. This is just the energy that is needed to put a baryon in a system or remove a baryon from a system. This phase diagram has very rich phase structure. There is a high temperature phase where quark and gluons, the fundamental building blocks of visible matter, are in free state. We call it quark-gluon plasma. A low temperature phase where quark and gluons are confined inside particles such as protons, neutrons, pions, kaons, in general called as hadrons. So that's the hadronic phase. At small chemical potentials, this transition is a crossover. It's a smooth transition, not a phase transition. At large baryonic chemical potential, it could be first order. And the point where the first order phase transition ends and crossover starts is a second order phase transition point, and it's the QCD critical point. Now, this is a landmark point because if we can get this point discovered, then that will make the phase diagram a reality. Why? Because on the top of it is the high temperature quark-gluon plasma. Below it is the hadronic phase. On the right of it is first order. On the left of it is crossover. And that's where the program is getting focused. If we manage to do that, perhaps one day this would also become part of the textbooks. How do we experimentally realize this phase diagram? We need accelerators where we collide heavy ions at very high energies. That takes us to temperatures of the order of 10 to the power 12 Kelvin, where matter melts into its fundamental constituents, quarks and gluons, and then as it cools, it hadronizes. So you have this phase transition possible in these collisions. One thing to notice is as you change the collision energy, as you go to higher collision energy of these heavy ions, the temperature increases, baryonic chemical potential decreases. Those are exactly the x and y axis of the phase diagram. So by changing the collision energy, you have access to large parts of this phase diagram. And that is how we proposed at RIC a beam energy scan program, and whose results I will show. If you go along this y-axis and to high temperatures, you will reach situations which mimic a microsecond-old universe temperature conditions. If you go to moderate temperature and high baryonic chemical potential, you will reach astrophysical objects whose core is expected to have quark-gluon plasma. Now, is that all, or there is a first principle theory which suggests that this is possible? The first principle theory is based on QCD. It is calculated using lattice QCD, where the four-dimensional space and time are discretized in terms of lattice. The quarks sit on lattice sites, and the gluons are the links. And this formalism can calculate thermodynamic variables such as pressure, energy density, entropy density as a function of temperature. Let's only concentrate for now with this blue curve, energy density divided by T to the power 4. It somehow reminds us about Stefan-Boltzmann law. And if you do a computation to statistical mechanics, you can see that this quantity is proportional to the effective degrees of freedom the system has. So this blue curve diagram translates to how effective degrees of freedom changes with temperature. from small values to large values. So which system can have effective degrees of freedom small? These are the hadronic systems where quark and gluons are confined. For example, a box of pions has effective degrees of freedom 3. There are 3 kinds of pions. Which system can have large degrees of freedom? These are free system of quark and gluons because you have color degrees, flavor, spin, and that gives large degrees of freedom. So this first principle QCD calculation tells that if you cross a temperature of around 150 MeV, then you will make a transition to quark-gluon plasma from hadronic matter. So that has the theoretical footing. How do we do it? This data which I'll show you is from relativistic heavy ion collider, which is a facility which exists at Brookhaven National Laboratory in USA. It's a collider with a circumference of this is about 3.5 to 4 kilometers. And we collide heavy ions and at very large speeds. So you try to create the conditions, high temperature conditions to form quark-gluon plasma, and then it cools down to hadronic phase and you study these transitions. Now the challenge is that these femtoscale systems, both in size and in time. So that makes experiments very difficult. Ironically, for this femtoscale system, you need meter scale detectors, and it's a very complex system, and hence minds from many different parts of the world come together to build these experiments. The key to this is there are a few things which we have to measure accurately. One is we have to identify the particles produced in these collisions with high purity. And that we do, these charged particles lose energy through ionization process in the detectors. And for a given momentum, these relativistic particles, the loss depends on its mass, and that is how you identify the different kind of charged particles. The other technique is you make them pass through a fixed distance. The time taken depends, for a given momentum, depends on the mass of the particle. That's the time of flight technique. Also, the detector is kept inside a solenoidal magnetic field of about 0.5 Tesla that allows us to have accurate momentum measurements. And we have some uniform kinematic acceptance to do our studies. The next thing is, what is the observable? There are many observables. The one that I picked up to discuss here is one which can be measured in experiment and has direct relation to what can be calculated in theory. So the observable is net proton number distribution. One collision is one event. In that event, you have many particles produced. You identify how many protons are produced, how many antiprotons are produced, and you take a difference and fill the histograms collision by collision or event by event. The shape of this distribution is governed by the moments of the distribution. Mean is the first moment, variance second, skewness third, kurtosis fourth. And what we found is the product of moments or ratios of cumulants of the distribution are related to ratios of susceptibility which can be computed in theory. That is direct one-to-one correspondence. And this we showed here. These are skewness times standard deviation, kurtosis times variance as a function of collision energy. Red points are data. Open points are first principle QCD calculations. Beautiful agreement between theory and data showing QCD is the theory of strong interactions in non-perturbative regime, finite temperature. Of course, there are some caveats, assumptions which one needs to keep in mind when you do the comparison. But the key is you can measure the left-hand side and you can calculate in the right-hand side. So now I will walk you through what we have concluded on the phase structure. First, all these make sense if we have formed a thermal system. Now, how do we prove there is thermalization? We take help of model and data. Now, the cumulants of those distributions, multiplicity distributions, are related to susceptibilities. I just now discussed. Susceptibilities can be computed in theory by taking derivatives of pressure with respect to chemical potential. Now you do that and you have the first order moments, second order, third order, fourth order, and then you calculate, you take the model is a statistical model assuming thermodynamic equilibrium and a grand canonical ensemble picture. And the data minus model divided by uncertainties are plotted here. This is as a representative for 200 GeV, one collision energy, 39 GeV. You can see there is excellent agreement between a thermal model and the data, and that's how we conclude that the system has thermalized. But the microscopic mechanism, how this fast thermalization happens in a femtoscale system, is not yet understood fully. Now, what are the temperatures that we reach? Here is the first principle QCD calculations extrapolated to a continuum limit in lattice. The lattice spacing goes to 0. And you find that the temperatures that they say the transition will take place is now precisely known. It's 156.5 MeV. 1 MeV is 10 to the power 10 Kelvin. What are the temperatures that we attained in our experiment? Since it's a thermal system, you expect the distribution population of particles as a function of its momentum or energy to be exponential. Then the slope of this distribution gives an idea of temperatures. The temperatures reached can be as large as 800 MeV, 4 times larger than the transition temperature. So we form coagulant plasma, it hadronizes as it cools, and we can study the phase structure. Now in the phase diagram, in the small part of the baryonic chemical potential, it is expected to be a crossover. This has been precisely known in theory. How? They calculate susceptibilities as a function of temperature. This is a quantity which changes with temperature for 3 different system volume. The volume varies by factor 8. What you see, the peak height and the width does not depend on the volume, and that rules out it's a first order or a second order. It's a smooth transition from hadronic to coagulant degrees of freedom. This theory, again, this lattice QCD, goes on to say that if you can experimentally measure the 6th order cumulant divided by variance, it should be negative at these temperatures. So do we see that in experiment? Here are the measurements. This is C6 by C2 of this net proton number multiplicity distribution as a function of collision energy. The values are negative. At low energies, there are large error bars, but broadly they are negative and consistent with expectation of crossover. At a very small energy, it's positive. Maybe the system did not make the transition, and that is under investigation. We have collected high statistics data to reduce the error bars here so that we can say how long is this crossover region. What about first order? Now, first order generally involves mixed phase. So there are 2 phases contributing to the multiplicity distribution. That makes the distribution bimodal. And then the mathematical property of this bimodal distribution is if you calculate the factorial moments, they should increase with order and flip sign. So that is the experimental signature. Now let us see what we get. This is a busy plot. This is collision energy, factorial moments, 4th order, 5th order, 6th order. I draw your attention to this 7.7 GeV because first order is expected at large baryonic chemical potential. That's the lowest collider energy we have. You can see it's positive, values of the order of 10 or less, large uncertainties. 5th order, it goes negative, values increase. 6th order, the values are large, but the error bars are also large. We have now high statistics data. We are analyzing it to reduce this to see if we get the signature of first order. Now coming to the last one, the critical point. Now this is something which is known very well in condensed matter systems. This is the phenomena of critical opalescence, where a transparent liquid turns milky because of large density fluctuations. We are trying to see similar behavior for strong interactions. Now, what are the predictions for that? These are the recent theory calculations which suggest that this is the region in the phase diagram where you expect the critical point to lie. It's actually a critical region, so we expect that the signals we could pick up even if we do not exactly pass through the critical point. What is the experimental signal? From a QCD-based model, it is predicted that if you look at 4th order fluctuations as a function of collision energy, then you should see a non-monotonic variation in this quantity. And what did we see a few years back with the first phase of the program? This is 4th order fluctuation, exactly C4 by C2 or kurtosis times variance, and you see a non-monotonic variation. This is we quantified at a level of 3 sigma only. The error bars are large, so we took a phase 2, and here are the result in the phase 2. This is the same C4 by C2 as a function of collision energy. These are the data points. These open points are a particular condition in data where we do not expect critical point to be there. There are 3 bands corresponding to 3 possible other baselines one is based on hydrodynamic calculations, the other on transport, the third is thermal. The best way is to look at is data minus reference by uncertainty, and you can see that at 20 GeV there seems to be a dip. If you take a data-driven baseline, it's about 5 sigma. Other models, then it can vary from 5 to about 2.5 sigma. That is where we stand. Lattice QCD calculations from first principles suggest something interesting would be between 10 to 30 GeV. However, we need a dynamical theory calculations in order to conclude the existence or non-existence of the critical point and what is the source of this deviation in data. So then I will summarize. So we have been carrying out a dedicated experiment in this facility for this particular project. The experiments have been running for 25 years now. It will end in March 2026. But when we proposed the beam energy scan program, it's roughly 15 years now. And we have been making measurements slowly and carefully. There are theory programs which are also being undertaken. What I showed you is that there are comparison of theory and thermal model that the system has attained thermalization. These are femtoscale systems, and how this fast thermalization happens, the microscopic physics behind this is still under debate and not known. There are clearly two distinct phases, the high temperature phase of quark and gluons, which are deconfined, the confined phase of hadronic matter, those are established. The crossover at low baryonic chemical potential is also fairly well established. I have shown you only one of the results. There is an intriguing experimental result at a level of 2 to 5 sigma depending on the choice of baseline. This is being very hotly debated in the field. Our papers, our last paper, the PRL, came out 2 months back. And we are still continuing to gather as much statistics as possible and perhaps move to high baryon density experiments. One of the facilities FAIR at GSI, the other is NICA at JNR, to establish the first order phase transitions. Studies are underway. Thank you for your attention.
Yeah, we have time, so we can take a couple of questions. Yeah.
In the phase diagram, you have colored superconductor. So are there experimental signatures of them?
No, normal matter can go only up to the nuclear matter, which is mass of proton, neutron, about 930 MeV. So how to push to beyond that is experimentally, our experiment cannot reach.
Whereas collapsing neutron stars, people talk about colored superconductors.
Could be. So maybe now that there are gravitational waves and things like that, we could access that. But in a laboratory scale,
it's not
we cannot reach there.
Also, I've heard that these questions give you like a flat pancake.
That is because these nuclei, which are usually spherical, are traveling with relativistic speed. So they are Lorentz contracted along the direction of motion. That's the picture. Of course, we cannot see that, but that's the picture which is shown in the illustrations. That's the reason.
Yeah, Avinash.
Vedant,
So, yeah.
one point which always worries me is that one is comparing experimental data with lattice QCD.
Yes.
But actually what worries to ultimately the continuum theory. The transition from lattice to continuum is something very subtle.
So I showed you one of the results from lattice. So now lattice, all lattice results try to go to the continuum limit. That is, this is somehow reducing lattice spacing. And these are their calculation data points, and then they extrapolate and see where they reach.
It is the extrapolation which is the, that's the...
If we have many points here, then it would be a better one. But these are also computationally very expensive calculations.
I know. That's the tough. So that's what it's about. Okay. Thank you.
Thank you.
So if there is no more question, then let us thank the speakers.
Thank you
once
very
again.
much. Thank you.